Welcome to the math record. Today I'll be covering Riemann sums. The idea of the Riemann sum is that sometimes finding integrals can be difficult, so what we do instead is that we're just going to approximate it. So there are generally three types. There is the right, there's the left, and there's the trapezoidal. Okay, now I'm going to explain each one. The left and right are pretty similar. So the left. So let's say we're using a quadratic curve. Now let's choose this point with this x value, this point with this x value. And let's say we want to choose two rectangles because we're going to approximate using rectangles. So we're going to choose 2 points, and these three are equally spaced. Now we do a left one. We're going to use the left height, so it's going to be here, here, here to here, and here to here. So we find the area of these three, which is going to approximate the area under this curve. Or instead, if we're using a right Riemann sum, similar, the same graph. Go back down, one here, and one here. Basically, we're going to use the right version. So instead of using this one, we're going to use this one. So that'll be from here to here, here to here, here to here. And getting the area of these three will give us the right version of the Riemann sum. Now, what about the trapezoidal? Well, basically, that's just the average between those two. So using the same curve, here to here. So the height of this, take the average of that. It's like probably somewhere right here. The average of this height and this height, which give us this height right here. The average of this height and this height, which give us maybe a height right here. And that will give us the area of our trapezoidal Riemann sum. And those are our three types. Okay, now let's try an example. So let's say f of x is equal to e to the power of x divided by x. Now let's say you want to find the area from x equals 1 to x equals 7. So we need to choose the amount of rectangles we want to use. And usually I like to choose one that fits my interval. So 7 minus 1 is 6. So our interval is 6. So let's say we choose three rectangles. 6 divided by 3 is 2. So we have a stepping size of 2. So we start at 1, step it by 2, that's 3. So we're at 3, step it by 2, that's 5. And we start at 5, step by 2 is 7. So these are our three intervals for our three rectangles. So our left, our right, and our trapezoidal. So the left one, we use the left points. So 1, 3, and 5. F of 1, plug in 1, that's e to 1 divided by 1 is e. F of 3, plug in 3, that's e to the power 3 divided by 3. F of 5, e to the power 5 divided by 5. Okay, now these are our heights. Now what is the base? Well, the base is just the length of our rectangle. So 1 to 3, that's the length of 2. 3 to 5, that's the length of 2. And 5 to 7, that's the length of 2. And that makes sense because our stepping size is 2. And that's what we chose for our Riemann sum because they're equally spaced. Now to do the right one, instead of using 1, 3, and 5, we use 3, 5, and 7. So f of 3, e to the power 3 divided by 3. F of 5, e to the power 5 divided by 5. F of 7, e to the power 7 divided by 7. What's the length of them? Well, it didn't change. It's still 2, 2, and 2. Times 2, times 2, times 2. And now for our trapezoidal, we take the average of each of them. So the first one is e to the power f of 1 plus f of 3. Take the average of those two. So it's just e plus e to the power 3 divided by 3 and a half. So 1/2 e plus e to the power 3 divided by 3. Now for the next one, that's f of 3 plus f of 5 divided by 2. So 1/2, and then e to the power 3 divided by 3 plus e to the power 5 divided by 5. Now for the last one, f of 5 plus f of 7, half of that, so 1/2 e to the power 5 plus e to the power 7. And those are our three of them. Now each of them has a length of 2, 2, and 2. So we can multiply each of these by 2. But as we know, there's 2 times 1/2, so we could kind of just cancel that out. Now you add up all these three areas, then we should get an area of 78.2 for our left using our calculator. For our right, we should get something about 386.1. And our trapezoidal should come out as something around 232.1. Okay, so as you see, there's a pretty big disparity between these two for the left and right. And that's, as I shown, was because if it's increasing and we choose the left, it's increasing and we choose the left, then this is an underestimation of our actual area because there's still stuff that's left over. Or if we choose a right one, we could see that we have an overestimation because there's sections right here that shouldn't be accounted for. And we see based on this graph, we have e to the power x. Exponentials increase really fast. So this slope is really, really steep. So when we get areas that have, let's say from here to here, and we have here, so let's make it really steep. We have an area from here to here, here to here, here to here. Let's say something right all the way up here, here to here. You see that the area is increasing each time. So whenever we're working with a Riemann sum, we need to determine if the function is increasing or decreasing. So then we could choose a better Riemann sum approximation. And usually trapezoidals are like average of them, so they're sometimes good, sometimes bad. Now, how do we get a more accurate Riemann sum? Well, basically, we use more triangles. So delete this. So we have a stepping size of 6. Let's instead use a stepping size. We have a interval of 6. Let's instead use 6 triangles. So we have a stepping size of 1. So we start at 1, add 1. So we start from 1 to x is equal to 7. So that's 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So 1, 2, 3, 4, 5, 6. We have those 6 triangles that we need to find for. And let's say we want to use a left Riemann sum because it's an underestimation. Now we plug in 1, we have e. We plug in 2, we have e squared divided by 2. Plug in 3, we have e cubed divided by 3, and etc. for 4, 5, and 6. So and then you can add them all up together, and if you use your calculator, it should come out as 123.7. And that is a pretty close approximation, well, close enough approximation to the actual one. And that's basically how you do it. And if you want to get even more precise, you could maybe have 6 divided by 12 rectangles, and we could have a stepping size of 1/2. So the more triangles you use, the more work you have to do, but the better approximation you get. Well, thanks for watching, and that's basically it for this video. And in the next one, I'll be covering Newton's law of cooling and logistic functions.